Welcome to The Explainer. Today we're exploring a really fascinating paradox of our modern world. We live in this era of hyper-advanced technology, right? Our global economy, our military power, even our daily commutes, they all absolutely rely on this invisible network of satellites orbiting thousands of miles above our heads. But what happens when that highly fragile thread of digital navigation gets cut? How do we find our way when the screens go totally dark? Well, the answer, incredibly, requires us to look backwards, to the most ancient navigational failsafe we have, the stars.
Okay, let's dive right into this, because this fact is genuinely staggering. According to the UK Hydrographic Office, a transmitter putting out just 1.5 watts of power, literally less power than your standard plug-in LED nightlight, can completely knock out GPS signals for 30 kilometers. 30 kilometers. It instantly exposes the terrifying fragility of the systems we trust with our lives every single day.
And the crazy thing is, a total signal loss is just one piece of the puzzle here. There is a whole spectrum of invisible threats to our global navigation satellite systems, or GNSS. You've got your low-tech jamming and space weather like solar flares, sure. But the absolute most insidious threat is something called spoofing. Hackers can initiate what's known in the industry as a graceful degradation. So instead of triggering loud alarms on a ship's bridge by just cutting the signal, spoofing slowly, secretly shifts the vessel's apparent location on the digital map. The crew thinks they're perfectly on course, while they are actually being steered straight into danger and they have no idea.
To show you just how debilitating this actually is, consider this story. Back in 2008, a Trinity House vessel off the coast of England participated in a planned, deliberate GPS jamming exercise. Now, the crew knew exactly when and where this jam was going to happen. They were totally prepared for it. And yet, the very second the GPS went down, this modern ship was instantly paralyzed. They were completely unable to navigate and literally had to stop dead in the water.
So the crucial point is the contrast between these two systems. GNSS and GPS are absolute technological marvels. They give us highly precise, automatic, real-time positioning, but they are deeply, inherently vulnerable. Celestial navigation, on the flip side, is completely analog. It has lower precision and, yeah, it demands real skill in mathematical computation, but, and this is the absolute game changer for us today, it is mathematically unhackable, completely unjammable, and entirely immune to cyber warfare. I mean, you literally cannot hack the sun, the moon, or the stars.
Part 1. Navies look to the stars, resurrecting ancient maritime failsafes.
The timeline of the U.S. Navy perfectly captures this pivot back to ancient techniques. For centuries, celestial navigation was a standard, fundamental competency. But as GPS became ubiquitous, the Navy just phased it out, formally dropping it from all their curriculum by 2006. But look at the irony here. Just as the threat of cyberattacks and signal spoofing began skyrocketing, they realized their massive mistake. Less than a decade later, in 2015, they scrambled to reinstate it at the Naval Academy, and by 2017, it was back as a strict requirement for quartermasters. And this brilliantly illustrates why having that analog backup is so absolutely vital. Because when the chips are down, celestial navigation saves lives. Captain Bligh navigated 3,500 nautical miles to safety after the mutiny on the Bounty. Frank Worsley used pinpoint star sightings in just horrific weather to save Shackleton's expedition. And in modern times, you have Steve Callahan, who survived 76 days lost at sea, finding his course using a makeshift sextant constructed out of a pencil. When digital systems fail us, the stars simply do not.
But hey, we aren't completely abandoning technology either. Enter devices like the DS10 digital sextant. This thing is a brilliant bridge between ancient technique and modern convenience. It's a standalone instrument that takes a traditional star sighting, but then calculates the position instantly for you. No bulky nautical almanacs or endless mathematical tables required. And the best part? Because it's entirely self-contained, without any reliance on outside power grids or satellite signals, it is totally immune to a lightning strike or a malicious hacker.
Okay, so that covers our oceans, but it raises a really fascinating question. You see, the traditional sextant relies entirely on measuring the angle between a star and the ocean horizon. So, how do you navigate by the stars when there is no ocean horizon? Like, how do you navigate in the total vacuum of space?
Section 2. Apollo's Golden Age, Cosmic Navigation in the 1960s.
When cosmic navigation faced its ultimate test during the space race, astronauts obviously couldn't use a flat horizon. Instead, engineers developed space sextants. An astronaut would look through the optics and measure the angle between the curved edge of the Earth, or the Moon, and a specific background star. Because starlight is essentially parallel, measuring this angle puts the spacecraft somewhere on the surface of this giant, imaginary 3D cone extending out into space. By taking sightings of multiple stars, you create multiple intersecting cones. And exactly where those cones meet, that point in three-dimensional space is exactly where your spacecraft is. It's like a giant cosmic puzzle.
138. That is the exact number of manual sextant sightings astronaut Jim Lovell took during the historic 1968 Apollo 8 mission, the very first time humans ever left Earth orbit and traveled to the Moon. He took over 70 sightings on the way there and another 70 on the way back, essentially becoming the single most prolific celestial navigator in space history.
The navigation strategy for Apollo 8 was basically a masterclass in redundancy. The primary system relied on radio transmissions from ground control back on Earth. But the onboard celestial navigation was the ultimate bulletproof backup. It had to be there to prevent catastrophic blunders, to allow the crew to navigate when they flew around the dark side of the Moon and lost all radio contact, and frankly, to give the astronauts the confidence that they weren't entirely reliant on an invisible umbilical cord stretching hundreds of thousands of miles back to Houston. And Lovell's manual sightings were incredibly accurate, perfectly matching ground control to within 1/100th of a degree.
Now, what's really interesting about this is the sheer brevity of this era. This so-called golden age of manual celestial navigation in space effectively lasted only the first 10 hours of the Apollo 8 mission. After that 10-hour mark, mission control and the crew realized that the radio tracking techniques were actually so incredibly reliable that they could safely just take over as the primary method for good.
But they never abandoned the stars completely. They blended these techniques together, and the precision they achieved was just mind-blowing. By Apollo 12, just a year later, the navigation was so incredibly dialed in that astronauts Pete Conrad and Alan Bean landed their lunar module within actual walking distance of the Surveyor 3 robotic probe, which had just been sitting there on the Moon for over 2 years. They literally walked over and snipped a piece off to bring home. That's how accurate they were.
Section 3. Modern Space Star Trackers. Automating the stars. So, in today's era of new space, manual space sextants are pretty much a thing of the past. The modern equivalent is called a star tracker. It's essentially a highly advanced digital camera paired with a computer. It constantly captures images of the star fields around the spacecraft, compares those images instantly against a massive internal digital catalog of the cosmos, and tells the satellite's computer exactly which direction it is pointing. This attitude control is absolutely vital, by the way. Without it, a satellite can't keep its solar panels facing the sun or point its communication antennas back to us on Earth. Let's move on and see how this builds into real-world hardware today. Companies like Terma are creating entire specialized lineups of these devices. You have the robust T1 model, which is built for deep space and geostationary orbits. It's designed to survive 15 or more years in the absolute harshest radiation environments out there. Contrast that with the T3, which is aimed at the booming commercial low Earth orbit market. The T3 is a commercial off-the-shelf design that is smaller, lighter, and vastly more affordable to mass produce for those huge satellite swarms we're seeing today.
The engineering inside these trackers is just staggering. The T1, for instance, uses radiation-hardened aspherical optics and achieves thermal stability without even needing power-hungry active cooling systems. But the most mind-blowing spec? Its accuracy. 3.6 arc seconds. Okay, to put that into perspective, this tracker can detect a shift in the satellite's orientation as incredibly minute as the height of a single euro coin viewed from a full kilometer away. No way, right? But that is literally the level of precision we are getting from staring at the stars today.
And the industry is getting remarkably flexible too. Terra offers what they call a divorce by design approach. Basically, if you're building a satellite where every single gram of weight costs a fortune to launch, you don't actually have to buy their heavy computer hardware. You can just buy the Star Tracker software library independently and run it directly on the cameras and computers your satellite already has on board. It's a really brilliant way to slash costs and save precious weight.
So where does this ancient art of looking at the sky go next? Well, the new frontier is artificial intelligence. By integrating advanced AI algorithms into these star trackers, engineers are preparing to push attitude determination accuracy way beyond what traditional mathematical methods can achieve. AI is going to process the star fields faster, account for optical noise much better, and make this completely unhackable navigation method more robust than ever before.
From ancient mariners sailing the Pacific, to the Apollo astronauts rounding the dark side of the Moon, to AI-powered digital sensors keeping our modern satellites alive, one thing remains absolutely constant. When our most advanced, fragile technology fails us,
The universe provides the ultimate backup. It leaves us with this beautiful realization. As we push further and further into the unknown, the stars are no longer just our guides. They are our destination. So the next time you blindly follow your GPS, ask yourself, if the screen went completely dark right now, would you actually know how to look up? Thanks for joining me on this explainer. Keep looking up, and I'll catch you next time.